is here. I don't know Casey. Dale Bryan from Sustainable Plymouth. A lot of people are chiming in. So I guess we'll get started. I have a little introduction. Good afternoon. I'm Frank Mand. I'm a member of what we call here the Plymouth Saltwater Intrusion Task Force. Dramatic. One of the task force responsibility is storytelling. And today you're going to hear a story of what we think of as the unseen, but also the obvious, the nuisance and the nightmare, the everyday and the timeless. It's a story of little things which, if not paid attention to, can quickly evolve into world changers. Are we exaggerating? Perhaps, but consider that saltwater intrusion can result in the loss of the species you expect to find, the forest you expect to see, the water you thought was pure, and bottom line, the taxes you expect to pay. That's in part why this project has a dozen partners. Each partner has a distinct concern. One partner, the Plymouth Water Conservation Committee, is trying to dramatically reduce the per capita consumption of water in Plymouth. If what we abbreviate saltwater intrusion as SWI takes hold, that effort will be more important than ever. And we may learn a little bit more about that later today. The Six Ponds Improvement Association is another partner on this project. It's a community organization that works every day to ensure that the beautiful ponds that are the centerpiece of their neighborhoods retain their biodiversity and overall vitality. The Herring Pond Wampanoag tribe is another partner, and they can't help but see that threats like SWI are yet another insult to their homeland, which by definition is an insult to them. And then there is the municipality itself, partner number one in a way, and by extension, the state government, who have partnered with us on this project because they know that they can no longer afford to simply react to the environmental changes happening all around us. Several local officials are due to be with us today. I know I saw State Rep Kathleen Lenatra, and I believe Representative Matt Muratori is going to be here as well. I was hoping to see a few members of the Board of Select Persons in town. I don't see them yet, but hopefully they're going to be coming. But don't worry, today's presentations will have much more narrow focus than this introduction. Today you're going to hear the who, what, where, and why of saltwater intrusion, and then how what we have learned so far is being applied to coastal communities, and in particular to Plymouth in this project. We'll hear directly from two accomplished researchers in this field. First, from Dr. James Heiss, a faculty member in the Department of Environmental, Earth, and Atmospheric Sciences at UMass Lowell. Dr. Heiss will give us the who, what, where in a presentation entitled Saltwater Intrusion, Processes, Mitigation, and Prevention. Then our project scientific lead, Dr. David Boutt, full professor in the Department of Geosciences at the University of Massachusetts-Amherst, will go local in a presentation entitled Vulnerability Assessment in Plymouth, Massachusetts, Compounding Effects of Sea Level Rise on Water Quality and Aquifer Sustainability. In the wings, we also have Dr. Julia Guimond, I don't know if I pronounced it right, a postdoctoral fellow at Dalhousie University, and Dr. Holly Michael, the Unidel Fraser Russell Career Development Chair for the Environment and a professor at the University of Delaware. First apology of the day goes out preemptively to these accomplished academics because we don't have time to recount all the degrees, honors, positions, and papers that they've accumulated in their careers. We've provided a lengthier hard copy summary for those attending in person at the center, and we'll provide those as well to anyone online who requests it. So without further ado, let's get to it. Here to lay the foundation is Dr. James Heiss.
Great, thank you. Let me just share my screen. All right, so everybody can see this? Okay, great. Great, I'm happy to be here.
James, we can't see it on Zoom.
You can't see me on Zoom?
Can't see the presentation.
Slides.
Did you share the screen? I think you forgot to share your screen.
Check. How about now?
Yeah, that's
Yep.
great. Good.
Great. All right, so do you see the whole screen is the slide?
Yes.
Okay, great. So yeah, thank you, Frank, for the introduction. My presentation today is titled Saltwater Intrusion, how it occurs, how to mitigate it, and possibly how to prevent it. So fresh coastal groundwater is really important. About 100 million people in the US, particularly in counties along the coastline, depend on fresh groundwater. And they generally use it for drinking water, irrigation purposes, or for industrial purposes. So this map down here, if I can get my pointer, this is just showing the distribution of coastal population centers in the United States. And generally along the coastline, population densities tend to be very high. So fresh coastal groundwater is vulnerable to contamination. And that contamination can come through a variety of forms shown in that figure on the right. So it can come from agricultural practices, things like pesticides and nutrients that are applied to crops can make their way into the subsurface, shown here, contaminating groundwater supplies. It can also come from urban runoff of pollution that enters soils that contaminates groundwater. It can also come from kind of localized salt storage facilities shown there in the right. It can also come from coastal aquaculture due to the use of antibiotics. But by far the most widespread and most important groundwater contaminant out there, along the coastline anyway, is salt water. So you can see here that salt water under the ocean moves inland underground and encroaches inland to contaminate these water supply wells or irrigation wells. So the focus of this presentation is really on saltwater intrusion and the landward encroachment of that salt water as groundwater. So if we kind of take a closer look at the coastline and take a slice out of the coast and look at it from the side, this is what the distribution of groundwater would look like. So beneath land, right, there's fresh groundwater here, and underneath the ocean, there is saline groundwater or seawater. And when we talk about groundwater, we're talking about pore water that exists between individual sediment grains. So water that exists between sand grains or between gravels that make up our coastline. So there's a reason why there is a kind of an interface that forms between the salt and the fresh groundwater, and that is due to buoyant forces. So the fresh groundwater is less dense than the salty groundwater to the right, and that forms a saltwater interface. The fresh groundwater, because it's less, rather more buoyant, it wants to float on top of that salt water. So it kind of forms this lens shape right here. So when we think about the difference in density between the fresh groundwater and the salty groundwater, we can actually use a really simple relationship to estimate the depth to that saltwater freshwater interface. And that relationship is shown right here. It states that for every foot of freshwater above sea level here, there will be 40 feet of fresh groundwater below sea level. And so conversely, if the water table were to drop by 1 foot, that would mean that the thickness of this freshwater lens here would decrease by 40 feet. In other words, the depth to that saltwater freshwater interface would move up to the land surface by 40 feet. So for a very small amount of change in that water table elevation, there's going to be a correspondingly large change in the depth to that saltwater freshwater interface. And again, this is due to those buoyant forces that are at play here. So whenever that saltwater moves up closer to the surface, or if it intrudes inland, that is what we refer to as saltwater intrusion. So it's the encroachment of that seawater into freshwater, and that leads to salinization of the groundwater and a reduction of those freshwater resources. There's a variety of causes. So I'm going to go through kind of the different modes that lead to saltwater intrusion. So first up are some of the more natural causes. First, we have reduced groundwater recharge. So reduced groundwater recharge, right, there's precipitation. Some of that water runs off the land surface. Some of that enters the subsurface where it recharges the water table. If there's a reduction of that recharge, say seasonally, right, during the summer months, there's going to be less precip. and less groundwater recharge. Or if there's an expansion of impervious surfaces, parking lots, buildings, things of that nature, then there's going to be less precipitation reaching the water table. And that's going to, as I said a moment ago, it's going to result in the inland encroachment of that seawater. Another possible mode of saltwater intrusion is sea level rise. So as sea level rises, right, that disrupts that balance between land and sea, and that results in saltwater intrusion, both horizontally, as you can see here, but also vertically, because there will be parts of the land surface that are, or that would be originally fresh, that become inundated by saltwater. So there can be vertical saltwater intrusion as well. And then thirdly, storm surges is another mode of saltwater intrusion. So saltwater inundation of the land surface during a storm surge, right? That's going to infiltrate into the subsurface and contaminate those fresh groundwater supplies. So I have just a note there that storm surges are anticipated to increase in intensity in the future due to climate change, and possibly with an increase in frequency as well. So those are kind of the three key ways that groundwater can become contaminated naturally. This is just a screenshot of a storm surge in Boutt Beach in Massachusetts. You can just see there that there's a lot of ocean water that is making its way far inland, and so that inundation of the land surface of saltwater, that seawater is going to infiltrate into the aquifer and contaminate it. So one of the ways that groundwater becomes contaminated by humans is just through pumping. So if there is a pumping well that is installed at the coastline, then that's going to act to draw up salt water into those pumping wells. And so I have another note there that says nearly all coastal cities are projected to grow in the coming decades. So we can expect that these effects on groundwater pumping and this upconing process, it's called, might be expected to increase as well. So you can kind of see that we started off with this originally very large fresh groundwater system that's been experiencing a drastic reduction in its overall size and volume. So there are some kind of complicating factors that we also should think about as well. So on the right there, I show that the saltwater freshwater interface is a really sharp transition zone, but really that's not the case. It's actually a mixing zone. And in this diagram, I'm showing that it's still even a pretty narrow mixing zone, but in reality, it can vary in thickness quite a bit. So this is a cross section of the Biscayne aquifer that is used heavily to supply drinking water to the residents of Miami. And so over here to the right side, this is Biscayne Bay. This is the land surface here. And so if we look at the base of the aquifer, we see that the width of that transition zone, or that mixing zone, is about 2 miles. And as we get closer to Biscayne Bay, right, it narrows quite a bit down to about 2,000 feet. So the width of that mixing zone can vary, from location to location, but also vertically in a single aquifer. Another complicating factor is geology. So, right, we can have different layers of geology that have different levels of permeability. Here I'm showing kind of 2 low permeability units that are confining a region of fresh groundwater, and that those 2 confining units can act to channel fresh groundwater offshore, which is really interesting because if we were to install a well out here in the middle of the ocean, or at least offshore, it's possible that we can pick up or measure fresh groundwater offshore. Another so this is just an example. This is again the Floridian aquifer system, just to demonstrate that, right, the geology can be pretty complex. So we've got a superficial or a shallow unconfined aquifer here that has its own saltwater freshwater mixing zone. And then we can have multiple confined aquifers, each with their own saltwater freshwater interface. Okay, so a third complicating factor are dynamic forces. So these are things that result in changes to the position of the saltwater freshwater interface over time. So for example, right, there are seasonal changes in precipitation, and with those seasonal changes in precipitation, there will be seasonal changes in the elevation of the water table. So in the springtime, when there's snowmelt up here in Massachusetts, and when we have precipitation, right, the water table is going to be higher than in the summer when there's less precip. So the oscillating water table seasonally will result in a oscillating motion of that saltwater freshwater interface landward and seaward. The ocean can also be important as well. So right, changes in the ocean level due to tides, of course, sea level rise, but even over shorter time periods, there are seasonal changes in the ocean level that are going to affect that balance between the land and sea, and that are going to cause this interface to oscillate landward and seaward. So saltwater intrusion is it's a issue that really the entire country is facing. So here are just some examples of areas of the coastline where it is occurring. So here we are. This is Los Angeles. So the saltwater is in yellow here. This is the Gulf Coast of Alabama. Here's the intercoastal waterway that allows salt water to encroach up the waterway, which then seeps into the subsurface, contaminating the groundwater. This is Miami, Florida, example I showed a moment ago. Similarly, there's the Miami Canal that allows salt water to encroach up that canal. That, much like the intercoastal waterway, that seawater will infiltrate at the base of the canal and contaminate the groundwater. And here again is Cape May, New Jersey, again, just kind of highlighting the complexity of the geology that can be at play here. So this is just in the United States, but it's also an issue globally. So there are many studies that document saltwater intrusion along the global coast. So again, not just a US issue, but it's a global one. Down here, if you can see it, it's a bit cut off on my screen, but right, there's about 1 billion people that live within 10 meters of sea level. A large portion of them rely on groundwater for drinking water and irrigation. But what's I think is a little bit more striking is that there's, of that 1 billion, 230 million of them are within 1 meter at sea level, or they're pretty much at sea level. So there's millions, approximately 1 billion or so, that could be susceptible to saltwater intrusion. So I'm going to go through a couple examples here. So here's Cape Cod, right? We do have a bit of saltwater intrusion out here. These contours on this map are showing the elevation of the water table. So kind of in the center of Cape Cod, the water table is around 80 meters. This is a map showing all of the pumping wells on Cape Cod. And right, so Cape Cod, much like the aquifer system around Plymouth, is a sole source aquifer, meaning that everyone on Cape Cod gets their drinking water from the aquifer. And because of that, there can be saltwater intrusion. So if we take a slice across Cape Cod and look at it from the side, looking east, then we would see that groundwater might look something like this. So again, we have fresh water that's floating on top of the saltwater. And here we have a pumping well, and down here, this is an observation well just to track the salinity. Right, so when we pump from that pumping well, right, there's going to be salt water that moves up to that screen, potentially contaminating that well. Right, so there are some efforts out on the Cape done by the USGS to kind of track saltwater intrusion out there. So this is showing a time series over about 2 years of chloride concentrations at an observation well, just like this here. So this is showing, right, that when pumping starts in this area here, chloride concentrations increase, and then when the pump is turned off, chloride concentrations decrease as that saltwater cone recedes back downward. There is implications for these kinds of declines in water levels on in the mid-Atlantic region. So this is showing water table declines in Virginia. So this is showing from 1970 to 2010, there's a drop in water levels. And so the drop in those water levels, in this case around Virginia Beach, and also parts of New Jersey, have declines of about 100 feet. And this was before 1980. After 1980, there were some management practices that were applied that allowed these water levels to rebound. Another really well-known example of saltwater intrusion is again the Biscayne Aquifer in Florida. So this is showing, these plots on the right here are showing the inland extent of that saltwater underground. So this is 1904 here, 1946, it's encroaching farther landward, 1977, and in 1995, you can see there's a very large swath of the land that has undergone saltwater intrusion. Miami is a really good example of management that has worked out very well. So the USGS has an online salinity mapper tool that exists. And there are wells that line the coastline in Miami. And within those wells, there are sensors that transmit data about water levels and salinity in them back to the internet, where the USGS is mapping changes in water levels and salinity in real time. And so what they're finding is that there is salinity miles inland, or elevated salinity several miles inland from the coastline. So they kind of have these maps that they're creating, again, in real time to track the location of that saltwater freshwater interface at depth. There are some implications beyond just groundwater resources. One of them is the formation of these ghost forests. So when there's saltwater intrusion closer to the land surface, that saltwater serves as a poison to vegetation. So that vegetation dies and it becomes a ghost forest, as you can see here. And so this is also an issue related to saltwater intrusion. There are other sources of salt other than the ocean that can contribute to saltwater contamination. On the right side, I'm just showing two maps of New Hampshire. And in particular, this is showing chloride over about one decade. And generally, you can see that from 1995 to 2005, there's been an increase in chloride concentrations generally throughout the state. Okay, so what are some of the approaches that can be applied in order to mitigate or prevent some of this? Right, the overall goal, the ideal goal is to effectively manage these groundwater resources in a sustainable way, where they will last in the foreseeable future. So there are kind of four key approaches that I'd like to talk about, and I'm going to have a couple of examples for two of them. So first one, kind of the easiest one, is just manage groundwater pumping. It's the simplest, again, it's also the most cost-effective. One way to do this is to have a pumping well located near the coast, say in the winter when groundwater, fresh groundwater is more plentiful than summer. So we pump from the coastal well in the winter, we turn it off in the summer, and then switch to pumping groundwater farther inland in the summertime. So that's one way that we can manage saltwater intrusion. Right, so this requires, though, sustained monitoring and possibly coordinated decision-making. What I mean by sustained monitoring is that we need to have observation wells. Sometimes they're called sentinel wells. They kind of track whether or not saltwater is starting to approach our pumping well. And I have coordinated decision-making there, possibly across governing bodies, because it's possible that that inland well might cross or be far enough inland to be in a different municipality. So there could be some coordination across governing bodies there that might be necessary. One example of a successful managed groundwater pumping project is in the Chalk Aquifer in England. So in the top right, this is England. This is the Chalk Aquifer here. This is London. So we're kind of interested in this area in particular. In the Chalk Aquifer, it supplies about 70% of the water to the region. And so what they're doing to manage saltwater intrusion is to have 4 coastal wells in the winter that are pumping fresh groundwater. And then in the summer, they turn those wells off and switch to pump from 3 inland wells. And this has proven to be highly effective. They found that that alternating pumping scheme can or has caused the water levels to rebound by about 16 feet, and that's reduced saltwater intrusion. Another example of a kind of a successful groundwater management scheme is in New Jersey. So here we are, this is showing groundwater levels in New Jersey. And what they did is simply reduce their pumping rates, and they switched to surface water partially. And so this is showing water levels in 1988. And when they made those adjustments, they found that the groundwater rebounded quite a bit, in some areas up to 120 feet. So this kind of managed groundwater pumping can be successful. Another way to mitigate or even prevent saltwater intrusion is through artificial recharge. So the idea here is that an injection well is installed between the saltwater interface and the pumping well. And that injection well, right, there's fresh water that is injected down there that creates a hydraulic barrier to prevent saltwater intrusion. An example of this would be in Los Angeles. About 1/3 of the Los Angeles area relies on groundwater. And that groundwater is at risk of saltwater intrusion. So there's been some really good cooperation between the state, the county, and the city to install freshwater injection wells. And you can see here in this kind of 3D view, there are these yellow barriers here along the coastline. Those barriers are lines of freshwater injection wells that have been successful in mitigating that saltwater intrusion. So what does this require? This requires potentially a large freshwater source. And if there are already, or if the area is already strapped for freshwater, that can be an issue. The question becomes, where does that freshwater come from? It could come from surface water, rainwater, it could come from treated wastewater, or it could be from desalinized water. But of course, we know that desalinization is an expensive process, so that's something to consider as well. There are also physical obstructions that can be installed in the subsurface. Here I'm showing a subsurface dam or a barrier that can be placed ahead of that saltwater freshwater interface to prevent intrusion. There are a number of research papers out there that show that this can be successful. This is a laboratory experiment. This is a sand tank. So down here, it's about 3 feet rather. 3 feet long and about 1 foot high, right? And so this is a barrier that's preventing saltwater intrusion. There's other ways to study this type of mitigation measure too. We can use numerical or mathematical models to simulate these processes. An example of this would be in Japan. They've had a successful effort at this too. What does this require? Well, it can require coordinating with engineers, particularly civil and environmental engineers, and it involves the emplacement of hard infrastructure at depth, which can be expensive if the aquifer itself is very deep. There is also barrier pumping wells. So similar to the physical obstruction, it's possible to install pumping wells within the saltwater itself to intercept that intruding seawater. Right, and so again, there are some studies out there that show that this can be successful. This is another sand tank experiment. Here is that barrier pumping well that's preventing saltwater from intruding farther inland. This requires an area to dispose of the pumped saltwater. And you can't just dispose of it on the land surface because it would contaminate vegetation. An easy way, though, is to just dispose of it back into the ocean. But that could be an issue, though, if that pumping well is far inland. You need a way to pipe it offshore. The fourth approach is called aquifer storage and recovery. The way that this works is that during periods with abundant fresh water, we can inject that fresh water into the subsurface. And then during periods of high demand or during dry periods, we can then extract that fresh groundwater for use. What this requires is possible treatment of that pumped water due to mixing. In this conceptual model, this conceptual diagram is very simple. It shows, right, there's a really sharp interface here. But again, there's going to be mixing between that fresh groundwater and the salt water, which might need to be treated at the surface. Sometimes there are combined efforts that can be used. So if we were to use a recharge well combined with an extraction well, then that can be an effective way to do this. So sometimes there's no one way to mitigate or prevent saltwater intrusion. So that kind of brings us to investigating the physical processes, right? And so we need to understand how groundwater moves in coastal environments so that we can develop insightful mitigation strategies so that we know which method to apply. There are multiple ways that we can study groundwater systems. I'm just going to focus on one of the ways that can be used here. So mathematical modeling. This is a map view of Bangladesh. Bangladesh is located just to the west of India and kind of at the base of the Himalayan mountains. The population of Bangladesh is 160 million people. And the size of Bangladesh is about the size of Pennsylvania. So we're talking about a population about half the size of the United States in an area the size of Pennsylvania. So this is an incredibly densely populated country. Many of those people live at the coastlines, so they're highly vulnerable, or their drinking water wells rather are highly vulnerable to saltwater intrusion. If we were to take a kind of a cross section or a side view of the coastline in Bangladesh, then we might find that the geology could perhaps look like something like this, right? This is a theoretical distribution of what a complex system would look like in terms of geology, right? So we're looking at this is a side view on the left side. This is depth. So we have an ocean boundary here, and on the left side, this is the land surface. These mathematical models are used to simulate the movement or the encroachment of that saltwater inland. So we can incorporate this kind of complex geology into mathematical models to simulate the intrusion of saltwater. And so this is just showing kind of an example of saltwater intrusion in Bangladesh due to, I believe this is a 1 meter rise in sea level over about 50,000 years. So just an example of a numerical model here. And so these models are really powerful. They can be used to answer what I think are really important management questions, such as which mitigation measure that I just talked about a moment ago might be most suitable for a particular area. They can also be used to answer a question such as what is the estimated lag time between implementation of measures and improved water quality. They can also be used to answer a question such as for a range of management and climate change scenarios, where may the saltwater freshwater interface be located in X, Y, or Z years? So again, these mathematical models are really powerful and really helpful for decision making. So to summarize, saltwater intrusion is a pretty complex and it's a growing issue, not just in the US, but worldwide. And so to really mitigate and possibly prevent it, it really requires coordination between decision makers and those policymakers, as well as scientists and local communities. And from what I understand, everyone, at least that's in the room and those that are virtual, as well as those that are involved or will be participating in the event tomorrow, all three of these entities are being engaged. I think that's really wonderful. So I think this is a really great effort. It has a lot of foresight, and I think it has the potential to serve as kind of a model for other municipalities. So I'm happy to take any questions. Again, my colleagues on the line, David, Holly, and Julia, we're all happy to answer any questions that you might have.
Speak up.
So this is Brigitte Keene. Could I ask a question?
Sure.
Okay. Oh, there. Now you can see me, or I can see you. One of the things that I know from some of the volunteer work that I've done in Plymouth is that here in Plymouth, if you have a private well, you will 99.9% of the time have a private septic system. So what comes out of your well is going to go back into your septic system. But also, if you have a private septic system, you could also, other houses can be on a public water distribution, which is a mismatch. So because we're sort of 50-50 between private wells and public wells servicing the town, and we're not quite there with our septic system, we have a mismatch in the way that we recharge our aquifer. And I was just wondering if that mismatch has any impact on what you're discussing with saltwater intrusion.
Yeah, that's a really good point, an important question. And I think that kind of highlights the importance of community engagement and to educate those with private wells that it could be important for them to manage their pumping as well. So again, I think that's just that's where the community engagement comes in. And I think David might be talking about this a little bit later, but there are also implications for sea level rise on the efficiency of those septic systems. So I won't touch on it. I think David is going to talk about it, but that's another thing that I think community engagement and education could also be important for.
And just as a second part then of that sort of mismatch, it seems to me that from what you were saying, that really the management of the public wells is how we're going to be managing the private wells, which aren't dug as deeply as the public wells, but could be in proximity to the public pumping stations. So I think there's a little bit of a higher risk sometimes in the private wells, more so than those impacted by the saltwater intrusion that could be impacting the town. Saltwater intrusion from the town's pumping could first impact those with private wells. Does that make some sense to you, what I'm saying? Because they're not, because of the way that they're dug and they don't have the ability to manage testing in the same way that the town wells do. So anyway, statement, but I get concerned by this town and its reliance on about 60% of the population is on a septic system and about 40% of the population is on private wells. So we have a real mix and a real mismatch.
Yeah, that's a challenge. It looks like, Holly, do you have something to say there?
Yeah, if I could just comment on that, that's a really important observation. I was just going to comment that yes, I agree that it's the municipal wells that really have to be managed. The amount that's pumped by a single family well is really small. And similarly, what would come out of the septic system of a single house, even if they're on the municipal water, would be relatively small. But the issue is that you're pumping out of these large capacity municipal wells, and then you're distributing it out. And so whether it comes out of septic system or whether it goes to a wastewater treatment plant, it's not being recharged in the place where it's taken out, right? And so anytime you have that imbalance of water, you have this potential for seawater intrusion. And so one of the mitigation measures that James pointed out was actually injection of treated wastewater, which is something that can be done. I don't know if it would make sense in this case, but that is one way that some places have dealt with that imbalance of water issue. And the other thing you brought up is also really important, this issue of I don't know if it's an environmental justice issue, but thinking about who's vulnerable and what is that a result of. So like I said, the individual homeowner wells are really small capacity, but if they're located near the municipal well, then there is potential, especially if they're closer to the shore. So that's something that in my group we've actually done quite a bit of work on in Delaware, thinking about different users of water and how their use differentially affects other users. And in our case, it's more about irrigation wells that are closer to the coast, but it's also the case for private wells.
It's an interesting discussion because we've been querying people in the community about their wells and can we come visit you? Can we test your wells? And these are, again, the wells of private wells. And so they have less of an impact on the overall issue that we're discussing, but they are very impactful in terms of the data they can give us for doing those broader studies, which may in fact affect the municipal wells. So they're kind of a minority that can have a potentially large influence. And I will say positively that they do not feel that they are separate from this issue because municipal wells will be more impactful. They feel we're surprised by how open they are to coming to their homes and testing their wells and things like that. So it's an interesting contradiction there, but it's working out for us.
Yeah, that's great. The only thing I would just point out is that sometimes monitoring for saltwater intrusion. Oh, sorry, David, I shouldn't have. I just went. To the topic.
Go for it. Go for it.
But I was going to say that the hard thing about saltwater intrusion modeling often is that in order to actually monitor it, you have to get your well in the interface, right? Because if you're, a lot of the wells that you measure, the private wells are probably going to be fresh, and that's great, but it means that we still don't know exactly where the interface is and whether it's moving inland, so the key is to kind of get as close as you can to the coast with the testing that you're doing so that you can try and capture that gradient.
And that's what we are doing. We're being specific.
Mhm.
So I know David wanted to say something.
I was just going to follow up. I think the point that Holly made about the redistribution of the water and, coming from the municipal wells to the septic, the septic fields, that's really important. The existing USGS model of the aquifer does have within it a certain amount of return flows, and those return flows are spatially, they're different depending on where you are. And I think those are the types of things that are going to be important for understanding, where that interface or how the interface geometry could change in response to different management decisions based on what the town is thinking.
So just to finish up then my discussion, and then I'll sit in the back. One of the areas in town where we have that a huge amount of that mismatch is right at Whitehorse Beach in Manamet, where they are at sea level. The homes are at sea level, and they all have private septics. They all have private septics, but they're all on town water. And then the other area is Cedarville. So those are two areas that I think really they're right on the sea, and yet they're all on public water and private septics.
Yeah, and a little bit beyond the scope of this, though, is too, as sea level rises, the efficiency of those septic systems is going to degrade, especially near sea level, and then that's going to lead to other water quality issues in the coastal waters too.
Okay, great. I think we'll move on now to Dr. Boutt, and he essentially is going to take this discussion local.
All right, can you see my screen okay, everyone? Awesome. Frank, I'm getting a little bit of feedback maybe from your mic, but I think it's okay. James, awesome job. Thank you so much for doing all that. I'm gonna kind of jump off on where you left off and dig into kind of where we are with understanding the kind of is there a potential for saltwater intrusion in the town of Plymouth and the Plymouth Harbor aquifer system, and how are we kind of looking at this problem, and how are we looking into the future? So as James indicated, so much like on Cape Cod, the groundwater system that underlies the town of Plymouth and the region is a sole source aquifer system. And one of the really important characteristics of this aquifer system is it's very permeable, and it also has a very strong coupling between the surface water that's in the ponds and the wetlands, and that in, let's say, the groundwater aquifer. So when we're talking a lot about the sort of the saltwater intrusion and the impacts of, let's say, degradation of water quality in the aquifer, a lot of that really applies to, you know, the surrounding surface waters as well. So I'm going to show you a map that was generated from a USGS study, United States Geological Survey study done in the region, where what they did was they performed a numerical model, constructed a numerical model of the groundwater flow within the Plymouth Carver, what they call the Plymouth Carver Kingston Duxbury aquifer, which is the aquifer that surrounds or is underneath the town of Plymouth. What they did was they assessed to different the receptors of different, let's say, groundwater that's coming through the system. Where did that water originate from? Actually, Frank, I'm still seem to be getting a little bit of maybe it's not Frank.
I think it might be James. I think maybe James, if he turns.
Yeah, James, can you, is it possible to mute you all on the SEMBA side?
Yeah. Let's see.
Okay, how's that? That sounds better.
Is that better?
It's better.
Yeah, awesome. Thank you. I was hearing myself twice. So, okay. So what they did was they determined, the USGS in this numerical groundwater model, they determined where the water originated from, let's say from a pumping well or from some coastal water body. And let me show you what this looks like. So this is a map of the footprint of the Plymouth Carver Kingston Duxbury aquifer. The lines on here are contours of hydraulic head. So this is the water table elevation above sea level in feet. And the different colors represent the areas that the aquifer contributes to different parts of the or different receptors of that water. So all these blue things, and I'm giving you a legend here. Like if you look at like some of these blue areas, these are areas where there's some municipal wells in Wareham, and they're capturing water that falls in this kind of polygon here, this kind of linear feature. Likewise, for some of the wells here in Plymouth, over here in Manamet. And then the other colors on here, the ones that are in yellow is water that would fall into the aquifer and then discharge, for in this example here, into Beaver Dam Brook and then go into the ocean. The ones that are in orange are areas where water falls on the landscape, moves into the aquifer and goes directly to the ocean. And this piece is really important for what we're talking about, because this water, the water that's falling on the landscape,
recording in progress,
and coming into the bay is the water that is essentially keeping that saltwater interface where it is. And in this particular system, as I'll mention in a minute, there's significant amount of natural fresh water that comes directly into the bay, into Plymouth Bay, into Cape Cod Bay, through the aquifer. One of the focuses of our work here is really trying to understand how, as sea level rises in this region, how the aquifer plumbing and the interface position is going to change in response to that. Colleagues here at UMass-Amherst and down in Rutgers have been estimating the magnitudes of sea level rise in and around This was for the Boston region, but it extends pretty much to Cape Cod Bay, where under different types of warming scenario or emissions scenarios, going from kind of the low emission to high emission, we're going to be looking at anywhere from a 0.5 meter to upwards of almost 2 meters of sea level rise in this region by 2100. And that's going to have big impacts on all of those processes James mentioned in terms of, not only just the kind of the static sea level, but also these dynamic effects during nor'easters and other large impacts. So one of the important things about the impact of sea level rise on aquifer systems, it's not just the position of the interface that we care about. As in this example, this is from the Bay Area in California. They're way ahead of, I think, the rest of the United States, and really trying to understand how, when sea level rises, it not only causes the saltwater, let's say, interface to move landward, it also pushes the level of the fresh water up in the aquifer, such that in certain areas, let's say where you have a septic system, and in this dashed line, let's say that was the position of the fresh water below this person's septic system prior to sea level rise. As sea level rise happens, what happens is the freshwater level rises and can actually intercept and cause water quality degradation, or essentially inefficiency of those septic systems. So let's take a look at what we know now about saltwater intrusion and its impacts in Plymouth. Okay, so I'm going to step you through what we know now. Okay, we don't know a lot. I'll just be very honest, right? But we do have, one of the things that I think is going for the Plymouth region and that Southeast Massachusetts region in general is that it's a very humid environment, and there's significant amount of natural infiltration of water, of fresh water in the system through the aquifer. And so this is just a kind of another look at it. These are showing the elevation of the water table in red above sea level. And there's a large amount of groundwater that flows through the system that can kind of counteract those buoyancy forces that James had mentioned. This region sees somewhere on the order of almost 50 inches of precipitation annually. Almost half of that water infiltrates into the aquifer system, which is quite a lot for an aquifer. There's also another thing that will help limit the amount of saltwater intrusion, is that there's a significant amount of just natural groundwater discharge into the coastal water bodies, which has the propensity to push that interface further offshore, such that as sea level rise increases, we might move it laterally, but it might still not impact our freshwater resources. So this is a numerical model that we've been working with for the Plymouth Carver aquifer. It's kind of north is up in this direction. Here's Plymouth Bay here, Pine Hills, Manamet, and all of these arrows in this numerical simulation of groundwater flow are showing you that freshwater flow that's going offshore. And one of the areas I want to zoom into is in here, let's say in the Manamet area, where you see a lot of these arrows that are just pointing kind of towards the coast, okay, pointing offshore. And that is that lateral groundwater discharge that's pushing that water out into the bay. One of the other things that I think is is positive and will help. And as James was discussing the relative impacts of pumping on saltwater intrusion, is that the relative rates of groundwater extraction compared to the natural recharge in the system currently are fairly low. We're not stressing the aquifer at, like that's been happening in some of those other examples that James gave in Southern California or on other parts of the Atlantic coast south of us. Now that can change into the future, of course, but they're currently quite low. James mentioned this concept of upconing. Here's an example from Cape Cod, where this is a numerical simulation. Red is saltwater, blue is freshwater, and you can see the beginnings of kind of some, let's say, higher salinity, higher chloride concentrations in this well field associated with pumping. So those things can happen, especially even in these humid environments. And it's one of the things that we're trying to understand in this study. The other thing that I think we have going for us is that James mentioned some of those complicating factors, and one of the things was the geology. The aquifer, the Plymouth Carver aquifer, is mostly unconfined, meaning that it's got a single, let's say, conduit for water flow. Here's an example again out on Cape Cod, where in that system, if you have a let's say an area of lower permeability in whatever the stratigraphic unit is here, and if it's discontinuous, it actually can cause additional intrusion of salt water beyond, let's say, beyond this shallower system. We do have some evidence of discontinuous lower permeability units. This is a cross section down here. This is Plymouth Beach and the spit that goes out there towards downtown here. We do have geologic evidence that there are local confining units that are going to, I think, impact the potential distribution of saltwater in the system. So how do we improve our understanding of saltwater intrusion and sea level rise impacts in Plymouth? Well, we're taking a threefold process here. One is trying to understand what the current distribution of salinity or the amount of dissolved stuff in the aquifer, using both historical data from different entities, different stakeholders, as well as newly collected data as part of our collaborative partnership. So here's just a quick look at some of the data that we've been working with. These are chloride analyses. So chloride is one of the main anions in salt water. Chloride measurements can give you some indication of salinity. They can also be sourced from other sources, such as road salt, as James mentioned, or other salts through septic systems and just through anthropogenic activities. Here's a look at what we see. 250 milligrams per liter is the drinking water standard. Just so you understand, 35,000 milligrams per liter is what seawater looks like. These are very dilute waters. In Plymouth, there are some areas, especially up here in North Plymouth, where we have some elevated levels of chloride. Whether or not these are related to saltwater intrusion is still something to be worked out. But for the most part, most of the public water supplies within the region, and these are, some of these are close to the coast. A majority of them are far away from the coast, beyond that interface location that Holly mentioned. Another way for us to improve our understanding of the saltwater intrusion and sea level rise impacts in Plymouth is to improve our understanding of how what is the subsurface makeup, the subsurface geologic material. There's some really new, cool geologic mapping that's been done by the USGS, by the Massachusetts Geological Survey, and from some students in our group that are using some offshore seismic data. Seismic data helps us understand the distribution of different geologic deposits below Cape Cod Bay into the subsurface that can allow us to understand how that impacts or what that means for our onshore geology. One of the things that is really interesting that in this data set that we can talk more about is that underlying the Pine Hills region are these older geologic deposits that weren't related to the most recent glaciation, which formed the Plymouth Carver Aquifer and have impacts on the thickness of the aquifer, as well as possible locations of lower permeability units, which might impact how we model the saltwater intrusion. We've also been working with lots of subsurface geologic data and different boring logs. Each one of these colors here represents a place where a well was drilled into the ground and hit bedrock, where we have some stratigraphic information that allows us to kind of build a three-dimensional distribution of stratigraphy within this domain. And the final way that we're seeking to improve our understanding and kind of the focus, the majority focus of this work is to use numerical models, as James had introduced, to help understand aquifer ocean interactions and the impact of sea level rise on possible migration of saltwater into the freshwater system, as well as how the hydraulics of sea level rise could impact how the aquifer and ponds or aquifer and wetlands interact. So I mentioned earlier, this domain here that you're seeing is the footprint of the state-of-the-art USGS groundwater model for the Plymouth Carver Aquifer system. Blue is areas that's just contoured, like reflecting a higher elevation of the water table of hydraulic head, and red is lower. The arrows are just showing you the directions of groundwater flow. One of the major tasks, I'll talk about this in a second, in our work is to revise this model to incorporate the physics of how freshwater and saltwater interact, as well as incorporate new information about the stratigraphic architecture of the aquifer that will allow us to better predict into the future of how the saltwater interface might migrate. Now, there's a couple things that we're, not to get too much into the details, but we're working to revise this model for a number of different reasons. As I mentioned, the model doesn't incorporate the physics of fresh and saltwater interaction. It doesn't incorporate any sea level rise into it. There are some other issues that I'll mention in a second. This just gives you a sense for what the numerical model looks like. Basically, in these models, you divide up the earth into cells and into like volumes of different sizes. You specify material properties. For example, that discussion that we were just having about the redistribution of water from, let's say, pumping wells and then into like infiltration galleries or infiltration basins where the water goes back into the subsurface. This model has some of that piece of information. One of the things that's a major issue that we found starting this project is that the calibrated model from the USGS does a really bad job of representing the water table near the coast. This is the land surface here, land surface cell. This is the calibrated model from the United States Geological Survey. All of these, the water table here is way above the land surface, which is in this particular environment really not physical. Part of the reason that this is happening is a lot of the work that the USGS was doing had to do with municipal wells, which are way back here. And they didn't really care about what was happening near the coast. We do, so we have to revise and treat the model and make some changes to incorporate. So the overall objective of this MVP project is to assess the impacts of saltwater intrusion into the freshwater aquifer. And we're going to do that not only by looking at what the current distribution of salinity is within the aquifer system, trying to understand that, trying to perhaps understand the different sources of salinity, and then develop a forward-looking numerical model where we can look at scenarios of sea level rise, freshwater extraction, and try to understand what are some of the possible scenarios looking forward. So work that's ongoing right now in our project is assessing the possible location of the freshwater interface in the region, just using the simple calculation, one of the simple calculations that James showed earlier, that kind of 40 for every 1 foot of fresh water, you got 40 feet of fresh water below that. We're refining the existing hydrogeologic model using some new data, new conceptualization. And then we're currently in the process of developing the groundwater flow model that can incorporate the saltwater impact. So just kind of a preview of kind of what we're up to. All of these areas that you see colored here, going from red to blue, are areas that are within a foot to 10 feet. The water table is above the land surface. So these are all the areas where we would expect at some reasonable depth, kind of on the 40 to 400 feet, where we would start to find some salt water in those areas. Now, this is just a kind of a static calculation of what that interface might look like. One of the things I think that you can see here, and I think one of the things that's actually very is I think a good thing, is that there's quite a lot of topography, not that far inland, that will prevent let's say far migration of the interface under different scenarios. So the year 2 of this work, once we have the new groundwater flow model, then we start to look at different scenarios of sea level rise, of different freshwater use, and how that impacts not only the migration of the freshwater interface, but also how the hydraulic effects of sea level rise can impact the interaction between freshwater and the salt water in those systems. So just to kind of touch a little bit on what we expect as far as outcomes and products, I think one of the biggest things, and this is, I hope, will live beyond even the saltwater freshwater modeling, is that we're going to be updating this groundwater flow model, making some significant modifications that I think can be a tool for the municipality, other stakeholders in the region, that can use that for not only looking at saltwater intrusion, but also other water issues within the region. We're going to be incorporating some of the most recent sea level rise scenarios. My colleagues here at UMass are really developing the best scenarios of sea level rise for Boston and the greater metropolitan area that we're going to incorporate into our models. And then that will lead into uncertainty bounded predictions of saltwater, fresh saltwater intrusion into the system and how that could impact water quality. And then coming back to some of the things that James was mentioning at the end of his presentation, series of recommendations, strategies, suggestions for mitigating impacts on sea level rise on water resources. It could be, as simple as thinking about, changing the way that, let's say the way that fresh water is used in terms of timing of the, in the year, to thinking about maybe abandoning certain municipal wells and choosing other locations that have less of an impact on the interface. And with that, I'll open it up for questions, and I thank you all for your time.
So David, this is Hampton.
Hey, Anthony.
How you doing?
Good.
We've one of the things that your slide, and I know that this is a Plymouth-based project. One of the things that I've often wondered about is the western extent of the Plymouth Carver, Kingston, Duxbury aquifer.
Yeah.
And the northern extent. We know that it goes down to into Wareham and so on, and communicates, would generally communicate with the sole source on the Cape, but that's not currently the case. But what's the western and northern extent of our aquifer? And I noted in your last slide, or near to last graphic of the aquifer, that the highest elevation of the water table was up to the northwest, which is really wonderful for us, in that it provides the elevation that will drive the flows down into the rest of the town. How far west does it go, and what's the I'll say the boundary layer to the west?
Yeah. So can you see my screen still?
No.
No.
I'm sorry. I turned it off. How about now? All right. All right. So this, we'll just use this map. In groundwater, in hydrogeology or groundwater systems, we define what we call a divide between water that would flow, let's say, one direction versus the other, based on the gradient or the magnitude of the water table, how high the water table is to relative to other places. So what I'm going to do is I'm just going to draw kind of a rough line through here, and this just kind of a first cut. So essentially, water that fell to the southwest on this side of this line would fall and go into Buzzards Bay. Okay, water that fell here is going to go towards Cape Cod Bay and Plymouth Bay. All right, and things get a little bit more complicated here because of there's the town brook and some of the streams and things like that. But basically, this is that divide. So if when when we're refining this model, we're primarily looking at things that are happening to this side of that divide. Now, because this is basically like a big mound of water, and if you start to change, let's say, the natural recharge into the system, the position of that divide can change, but primarily that's going to kind of separate out groundwater flow that's going to head out in this direction versus down in this direction. You can actually see, you can kind of see these flow lines captured by the wells here. And actually, there's some halfway pond. I'm not sure. Does it go around this way? It must go around that way.
Yeah, halfway pond goes into the Buzzard Cave.
Oh, it does. Okay. All right. Well, I will delete my drawing here. But so that divide where you're going to, it can be obviously impacted by where that surface water is and where, in those flow lines. But yeah, that's the general. And as you move north, things get a little bit more complicated, but that would hold.
Okay. Thank you.
Yeah.
So David, could I ask you just another question? Actually,
Yeah.
an observation.
Yeah.
So I spent about 3 years analyzing well testing water in Plymouth as part of my responsibilities on the Board of Health.
Yep.
And we began to insist for every well, for every septic upgrade, local upgrade approvals, that we would have a well test.
Yeah.
So in areas that are heavily septic dependent,
Yeah.
well test we got for the most part was over 250 milligrams. That was your cutoff. That's what the cutoff
Yeah.
is. And of course it has the little asterisk that says this doesn't impact your health.
Right.
But it does, if you have hypertension, impact your health. But here's what I want to mention is that many of these areas that have lots of septic systems also have private wells.
Mm-hmm.
And they use water softeners. And as you know, those are saline-based water softeners. So those highly septic dependent areas where there are wells and not town water, and there are water softeners, I went through hundreds of well tests because that was my responsibility on the Board of Health, and they were always above 250 milligrams.
Huh.
So I think you need to take that into account because otherwise you're going to have a bias in your data for those areas where you're doing well tests and you're coming up with 300, 400, 500, because you're going to, 4 houses down, they have a septic system that's pumping a whole lot of saline from their water softener.
Mm-hmm. Mm-hmm. Yeah, that's a good point. It's something that there are some of the analyses of, let's say, just the salinity, we can rule out different sources by using so there's in seawater, there's certain signatures of ions. We can look at things like chloride and bromide, for example. And that ratio is going to look one way for salt water. It's going to look very different than let's say chloride that's coming from magnesium chloride, from road salt or sodium chloride or some treatment. Now, we can't do that for everything. So I think with those salinity measurements, I think we're working on the assumption that it's going to be a little bit messy, and it's going to be kind of a baseline of, okay, here's what we understand about the salinity distribution in the system. And I have no doubt that I think in many of these areas, I think there's going to be a stronger either road salt or even like a sea spray signature than there is going to be, the upconing of salt water into the system. So
Mhm.
thank you for, I think that's a really, trying to tease out those different sources. It's going to be complicated in
Yeah,
that setting.
I'll tell you to attest, the salinity was high on our well test, and all that data sits there in the Board of Health. Some of it isn't cross-referenced in the way that they file data, but it's there over many years of the well tests that accompany the local upgrade approvals for the septic systems. So it's there. So anyway, thank you.
David, we have Eric Cody online with us. He's the chairman of the Plymouth Water Conservation Committee.
Awesome.
And they're involved right now in a very major effort to reduce the per capita, as I mentioned in the introduction, use of water in Plymouth. So I think he'll come on, I think, but could you elaborate a little bit about how this study will help other agencies and the town manage their water supplies? And then maybe Eric can say something.
Yeah. Hi, Eric. I think one of the biggest things is trying to understand, looking into the future, how how freshwater use in the aquifer could impact let's say the migration of the interface or even saltwater intrusion. So I think by looking at some of these different scenarios, looking into the future of not only how we think the amount of water that's going to be used in the basin, how much of that water is going to be returned into the system from either septic or other wastewater treatment plants, and how that might impact where you think you could perhaps put new water supplies in. Now, one of the challenges with that, we had a call a few months ago with a local consultant that works at Horsley Witten, Neil Price. And, even now they're up against major restrictions of where you could actually put in new water supply wells. And I think that's going to be the challenge in the future, is trying to find places where, if we have areas where we think there's going to be issues with perhaps saltwater intrusion, is trying to find alternate locations to put new capacity in. I think the modeling that's been done by the USGS to date, the modeling that we're doing on this project is going to, I think, help give some guidance on that. And it could even help drive some changes in the way that people use water within the aquifer.
I think we might have. Eric, are you there?
I am here.
Oh, great.
All right, so I assume that's my
Your cue.
just keep talking. I'll be brief. This has been, I know you've been on the Zoom quite a while, but I'll only take 2 or 3 minutes to tell you where the Water Conservation Committee stands. It was formed at the end of 2020 by the Select Board. Some of us in town felt that the 2019 draft Water Master Plan relied too exclusively on drilling new wells and failed to tap into conservation as a equivalent water resource. So that's where we came from. Can I share my screen? If so, I'll put up just a couple of charts. Can everybody see that?
Yes.
Okay. Just a few slides. Our work dovetails very closely with this project. We're concerned about saltwater infiltration, as well as a host of other threat factors, many of which are related to climate change generally. Lower groundwater levels, PFAS contamination of the aquifer. Our sense as a committee is that there's a lot of complacency in town about both the quantity and quality of our freshwater supplies, and we think that that's short-sighted. Our target is everyone in the town of Plymouth, not just people, the 15,000 customers on the town water system. Our goals, which were self-developed because we got no direction from the select board when they created the committee, obviously first and foremost to come up with a water conservation plan, help the town comply with its Water Management Act permit in both basins of the DEP, minimize withdrawals from the aquifer from both the public system and private wells, as well as private water systems in town, defer the need for new wells. Education awareness has become a really big part of what we're doing. We have found that people are just not aware of the precious nature of our freshwater supplies. And one of the things that Dan Gorsuch, a member of the committee, is beating on is we really, with all the growth that's going on in town, we really need to make sure that water conservation becomes integrated into the planning and development process here. This week, and a few of you have seen this, we released our first water conservation planning framework. It's about a 20-page document. My email's on the next chart, so we'll send it to anybody who wants it. But this document was intended to kindle a community conversation about water conservation, raise awareness, find out what people are interested in doing. We believe that a 15% reduction in total water withdrawals from the aquifer is feasible and probably easily achievable over the long run. And by that, we mean 15 years. This conservation planning framework document includes the sort of analytics of how we develop that 15% number. Frankly, I think it's closer than 20% if we get serious about this. And by the way, I have 40 years experience in demand management programs in the electric utility segment. So this is easy by comparison. If we were able to reduce water consumption in town by 15% over the long run, that's between 230 million and 300 million gallons a year that we would not be withdrawing from the sole source aquifer. We've looked at what kind of programs will get us there. Outdoor watering is by far the prime target. Monthly water use on the town system is 80 to 100% higher in the summer than the winter months. We're going to implement a pilot program this summer to see if we can change people's behavior, some of the highest residential outdoor watering people in town. To give you an idea of how dramatic the distribution of water usage is, if you took my wife and I are in a two-person household, we're very low water users. There are people in town who use 100 to 150 times the amount of water that we do. So that's what we're looking at. Unfortunately, we had wanted to produce a water conservation plan by this point in time, but there are, I guess I'd call them IT barriers, data barriers that exist in the metering data that preclude us from getting the kind of flexible access to individual customer data that we really need to plan programs, plan, implement, and evaluate programs. So that we're working closely with the Water Division and Public Works Department to overcome those. We actually have a workaround. We're actually creating a spreadsheet as I speak that'll have 60,000 data records in it for purposes of this summer program we're planning. So I'm hopeful that by the end of this year, we will actually have a water conservation plan that will be credible, defensible, and will verify this 15% sort of number that's currently estimated from the top down, verify it from the bottom up, showing the actual programs that we think can be depended upon and the customer participation rates that will get us to 15% over the long run. It's other communities have shown that this is doable. Plymouth has a lot of low-hanging fruit, so we're optimistic about this. We do think, I've been talking to Frank and Charles Heller about how to proceed with this, and we're going to be discussing at our committee meeting this coming week whether or not we want to hold a community forum like this, specifically focused on water conservation. But stay tuned for that. If anybody wants a copy of this planning framework document, just drop an email to this email address. We also have a very detailed evaluation report on the pilot program we ran last summer on rain barrels. That was kind of a mixed bag, but we learned a lot from it, and we set this evaluation report sets the standard for evaluations we're going to do on all of the pilot programs that we roll out here in Plymouth going forward. So in a nutshell, that's where we are. We'd encourage anyone to send us ideas and input. And if you want copies of the latest product, just drop us an email. And I'm happy to answer your questions if there's a few.
Thanks, Eric. One thing that just came to mind too is, when we're looking at some of these future forward-looking models, we can look at what sort of impacts would a 15 to 20% reduction in the freshwater use have on the system. And I think that could be informative for at least getting a sense. I mean, I know it's going to make obviously a big difference for water levels and things like that, but it would be interesting to see what that means for some of the fluxes that we're calculating and interface geometries and things like that.
Now I agree with you that that could be pretty challenging to do. This Plymouth's water system, the public water system, is one of the most complex and expansive in the Commonwealth.
Mhm.
They draw water from 13 wells at 11 sites.
Mhm.
So actually how the wells and the tanks get dispatched in an operational sense varies widely
Mhm.
on season of the year and the operating conditions. So how you'd actually specify the sort of scenario for that kind of modeling effort
Yeah.
is beyond my pay grade, but that's something that I think Peter Gordon, the water superintendent, might be able to help with.
Yeah, well, I mean, to some extent, I think the USGS did a bit of legwork on that, because all of those fluxes are included in their 20. They have a 2030 build out model, and I don't think we have to make it too overly complicated. But thinking about, okay, can we threshold or cut back some of the annual discharge, let's say, or summer pumping or something like that.
Well, it's a great idea nonetheless.
Thanks, Eric.
David, Kathy Lenatra, who's a state representative, and she represents more than Plymouth. I think she has several communities. She had to leave, but she asked me to have you respond to her concern or hope that some of the models that you're reworking and things like that will be available, and will they be relevant as well to other communities in the area?
I think so. I mean, I think we're going to be working off of the USGS model footprint that goes obviously beyond Plymouth, and we've had a number of conversations with local consultants that work for the different water authorities, be it in Wareham or Plymouth, that would much appreciate having access to a revised hydrogeologic model. You would be like, there are a lot of consultants that don't have the time to spend clients' money, going and changing the model or fixing things that I think there would be a lot of interest, I think, in the community and the different stakeholders to have a model that could be updated, at least with some of the recent changes. At a minimum, that issue I mentioned about the water table being above the land surface, especially in some of those coastal areas, precludes this model being used for different purposes. So
Thank you.
Yeah, for sure.
Frank, I'd like to chime in if you don't mind while he's thinking about Kathy Lenatra's district. David, I just wanted to point out, and Hampton asked a little bit about the Northwest, that the USGS head of the aquifer is really got cut off at Silver Lake, but that's the head of the aquifer. And that's the very northwestern tip. And you have, I noticed on your map, an arrow going out to the Taunton River. While that's true, it's because, of Brockton's, 9 to 10 million gallon a day withdrawal from the lake. And I think it complicates things, but we do have a bathymetric survey of the lake showing its 80-foot depth. And I think that you would be interested in that if you don't already have it, and I'd love to show it to you. But it's complicated because that's the Brockton system. And, although DEP is working on it right now and Central Plymouth County Water District Commission is working on it right now, it's probably more complicated than you want to get into. But I'd love to be sure that it's not excluded because the Jones River is considered the northern boundary and Silver Lake's its headwater. So, just enough for what it's worth, Department.
Thank you.
Well, I don't know if we're out of questions. Does anyone else like to speak, ask a question or make a statement? Let me just say that we've been, I hope, we've been attempting to record this. I think there's a lot of valuable information that we're going to make available. It's available through the Pine Barrens Alliance. If you want to access that recording, it'll be available in the next day or so, probably. Or you can call us at 774-773-9982, the Pine Barrens Alliance phone, and we'll make sure that you get the link to that. We have all been on this a while, and I very much appreciate the presence of our esteemed academics here today. Any final words from anyone? So I guess we'll call that a day. Very much appreciated again. This is going to be a very valuable recording. I think we covered a lot of bases, and we'll do it again tomorrow.
Yeah. I was about to say, if you can maybe record it tomorrow if it didn't work out. So. Frank, you're muted, I think. All right. Well, thanks, everybody. I'll for those of you who be on tomorrow, I'll see you then. Ciao.
Bye.
Bye now. Safe?
Not really. Even if you put that end button there, it's.
On the right.